now let's go to chapter 10. I'm going to introduce the band theory for solids. So this is a way for us to, at least qualitatively, think about electron energies. And think about what makes some things a metal, some solids a metal, what thing makes some solids an insulator, and then in between, okay? So this is a method to at least qualitatively, for us, think about electron energies in metals, insulators, and what used to be called maybe semi-metals, and we might call these now semiconductors. Because we know a metal conducts electricity well, right? So if you look on the periodic table, you have this place, you have areas where you know there's metals like nickel has atomic number 28, copper is 29, zinc is 30, and then below those you have lead, 46, silver, cadmium. But then next to those, and then obviously you have things that are not considered metals, arsenic and silicon. But right next to these are a class of particles that are not exactly metals, but they're not exactly not metals. Okay, they're not argon or something like that. So gallium has atomic number 31, germanium is 32, indium 49. Let's write a couple of these. So these are metals, and we tend to call these things semi-metals. So why do we call them semi-metals? What is a, if I give you something, some substance, some solid, could you tell me if it was a metal or not? And how would you go about telling me it's a metal or it's not a metal? What do you think of if I say metal?
Metals are generally conductive and malleable and ductile.
Malleable and ductile, yeah. So it means they're not real brittle, right? For example, if I give you a big chunk of graphite, would you say it's a metal? What do you think? Why would you not say? You guys know what graphite, like pencil lead, right?
Yeah.
Why would you say that's not a metal?
Well, it doesn't have sort of those like free moving electrons, so if I tried to run a current through it, it wouldn't work so well.
How do you know?
I guess I don't until I try it.
It's too brittle.
I thought graphite
brittle.
could conduct electricity to some extent.
Is this something like
Not as well as a metal.
Yes. So this is the point. So we think of metals as shiny, right? You can't shine light through them. They are somewhat malleable. Right? You take nickel and we pound it into different shapes. It doesn't just break. Same thing with silver and stuff like that. You can make silver wire and all this stuff. So metals tend to be malleable They tend to be sort of shiny. You can buff them up. But yeah, graphite, I would say, breaks easy. Maybe it conducts electricity a little bit, maybe not great. So maybe it's a semi-metal. Okay. So the point is, it's a little bit shadowy. You're just trying to figure out what is something a metal or not a metal. Okay. That's why band theory helps us a little bit understand why we call some things a metal, some things not a metal. So the effort here is to really give us some insight into that, what we call a metal and what we call a non-metal. So before we get into actual band theory, let's review slightly covalent bonds. Okay, so when we were talking about a diatomic molecule and the covalent bonds, we had, for example, so for a diatomic molecule, this was the separation distance between the two atoms. And let's say this is the energy levels for the electrons. So we had electrons on each atom. We had atomic orbitals, and we're combining them to create a molecular orbital, right? So we combine atomic orbitals into molecular orbitals. Now, what happened was that we got a split. We got a symmetric and anti-symmetric wave function that led to a symmetric energy level, anti-symmetric energy level, right? Bonding, anti-bonding energy levels. So, for example, I'm just going to put in, let's say we have a 3s state here. We would get sort of this bonding and anti-bonding, different energy levels, okay? When they're far apart, separated far apart, they would have atomic orbitals 3s. They come in, they split, right? Anti-bonding level maybe. So I just want to remind you of the symmetric anti-symmetric wave function, molecular orbitals. Okay, now, for example, let's say we have sodium, and let's say we put these two sodium atoms together. Sodium has atomic number 11, so 1s squared, 2p2, 2p6. That's one shell, it's another shell, 6, 7, 8, 9, 10. So it has a 3 electron, 3s. So we bring two of these together. They maybe like to share, so they fill that 3s. We could get a covalent bond, right? Now, let's say 2, so 2 sodium, 2 Na atoms. But what's going to happen if we bring more than one, or more than 2 atoms together? What's going to happen if you bring 6 of them together. What do you think is going to happen? So you can combine those atomic orbitals in different ways, right? You get anti-symmetric and symmetric wave functions, but you're going to get more than one level, more than 2 levels, I mean. So they all might have had 3s electrons, all those atoms that they want to share, but it's going to lead to a wider number of possible energy levels. You have to figure out how much, but it's going to be more than 2, okay? So, I'll say more ways to combine atomic orbitals. More splitting of energy levels. Does that make sense? Any sense to you that would happen? Without going through a detailed calculation. What do you think? Buy that at least? Yeah. Okay. If you buy that, then what happens if you do many? Put a whole bunch moving sodium atoms closer together to create a solid, okay? That means you'll have some farther away. They're all not equal distance apart, right? So here's sort of the equilibrium distance. They would all like to be apart from each other. But whenever you put many together, you're going to get a lot of different possible energy levels that the 3s will split into, okay? So, with many atoms making a lot of bonds, the 3s levels will split into many possible energies. So it's going to be so many that you can't really draw them, and you'll say it looks like a continuous range of energies between some minimum value and some larger value. So let's say here that was our equilibrium distance they would have liked to have been if they were the diatomic molecule. Okay? So we predict the, how do I want to say it? The splittings are so close that it looks like a continuous. Predict the splittings to be so close in energy. It looks like a continuous range of energies. You can call it a band. So it looks like a continuous range of energies, and we'll call it a band, energy band. how do you predict? We're going to predict something called the width of the band. And sort of what they do is they find sort of the minimum at the, where you would have that equilibrium distance if you had the diatomic molecule. And we kind of go straight up there, and we say, this is the bandwidth, this energy. So they can make some kind of bandwidth. Okay. Well, for example, sodium, it has, a sodium atom has a valence electron in the 3s state. That's the highest energy state that's occupied. But the atom has more states than that. They're just not occupied with electrons, right? It has 3p, 4d, all these possible energy states. Well, if you look at this big conglomeration of atoms all together, and you were trying to look at the energy levels for them, those 3p states will split into bands too. And so will the 4d states and all this, okay? So all the atomic orbital levels will split into bands when you put enough of these things together, enough of these atoms together. Okay. So we'll say there will also be 3p, 4s, 4p, 4d, so etc. They just might not be occupied by electrons, but you still have all these range of energies may be available. And some bands might overlap. So it can get quite complicated. So here's separation distance between things. So we might have had our 3s band here, and we might have 3p might split, look like that. So you might have an overlap of these bands. Okay. And of course, it depends on the separation distance of all the atoms and all that kind of stuff. So these bands might be partially filled, like the sodium. So they might not be filled at all. Only partially filled. So for example, the 3s, this, what we'll call the 3s band in sodium. Each sodium atom has one electron in the 3s state. It can have two, right? It can have up to two. So you might expect the 3s band to only be half filled when you put all these together. Each atom contributing one electron to that band, where they could have put two in. Okay? So for example, might expect the 3s band for sodium half full. Okay. Of course, we don't represent the bands in books like this. This is and messy. We draw them nice and neat in books and textbooks. So you'll see them drawn in a much more pleasing fashion than that. So this is how we represent the different energy bands. We'll draw them just like there's energy. Now we don't put another axis, we don't put distance between molecules. We just draw a nice rectangle. This might be my 3s band. Okay. If it's only half full, all we do is shade half of it. Shading indicates how much of the band is occupied, how much of the energy. Remember, this is energy. So shading indicates how much of the band is occupied by electrons. And if, for example, the 3p does overlap it, we just draw it like that. We might have a 3p state. Okay. And this is the energy width of that band. The bandwidth. This represents the bandwidth. It's an energy. It tells you how much energy that is in that 3s band. Remember, that comes back from all those 3s orbitals, atomic orbitals combining. Okay. One other thing about the bands here. Any questions that have arisen so far? Come to you. So we got this idealized version now, a representation of our band. And these are just energies, remember? These are energies from atomic orbitals all coming together. Okay? So again, the 3s band comes from all these 3s atomic orbitals, gives you sort of a continuous range of impossible energies for the electrons, 3p from the 3p orbitals, and so on. Okay, they might overlap and they might not. If we look at just the 3s orbital again here for sodium, I expect it. I expect it to be half full maybe because we only have one electron for each atom in the 3s state. So it's half full. Okay. If we plot on this, so I'm going to make another plot. This is energy. I'm going to make on this scale here, I'm going to plot the Fermi-Dirac distribution. Okay. So what do we see? What is the Fermi? And we're going to say the temperature of this is above 0. Okay. So what we would see, the biggest that can be is 1. And if you remember what this distribution looked like, so these are all occupied, all these energies are occupied, and then until you get to here. So the distribution tends to look like that. So it must look something like that. Okay? You think back to that. So this is, maybe I put my 1 here. So 1/2 is right here. That tends to be really close, and probably should be right at that. So this energy right here for this would be the Fermi energy. So Fermi energy tends to be at the top of that valence band. If you have a this would actually, sodium is what? Is sodium a metal or is sodium a something else? What do you think of as sodium?
It's a metal.
It's a metal. Sodium's a metal. So what makes a metal? So what this means is you have all these different energy levels occupied by electrons up to this, whatever this energy is. This Fermi energy. Okay? Now, so let's make that comment. All energy occupied by electrons up to EF in this case. I should also note that a partially filled band, it's partially filled with electrons, we call it the valence band. Okay? It can be partially full or full. So valence band is the band, the highest energy band. Partially filled or fully filled with electrons. So this would be a valence band for us here. What we'll call a conduction band. Conduction band is going to be the next highest empty band. Next band above the valence band. That is empty. No electrons. Okay? But if you look at this in this valence band here, it's only partially filled. So let's say we have an electron that has this energy. What's going to make it a conductor? What makes a conductor a conductor is that if you put an electric field in that thing, if we take our piece of metal and we attach it to a battery, we set up an electric field in there, and if the particles move in there because they're in that electric field, it's a conductor, right? So for the particles to move in a conductor, the charges to move have to give them energy. We have to give them kinetic energy, right? We're giving them energy in the form of kinetic energy. For charges to move in a conductor, we have to give them kinetic energy. We do that by setting up an electric field in there, a force on them. So we give them kinetic energy. Well, if this electron at the top of energy here, does it have room to gain any energy? Yeah, there's plenty of space here. There's plenty of energy levels possible for it here. So it's very easy to give this an electron that has this energy. It's very easy to give it a little more energy. Okay? So easy to give electron with this energy. A little more. So this is probably going to be a conductor. If we put an electric field in this, all these electrons can easily just rise up and get a little energy. Okay? Maybe it's not a great conductor. It depends on how much space is available. Can we give a lot of electrons energy? Or just a few? Okay. So this might be a good conductor. Here would be another example. Even if we have, and actually sodium looks more like this, we have the 3s. And matter of fact, we have a 2p that overlaps. I mean, 3p that overlaps. And only part of this is filled. So this is going to be a great conductor because we can move easily all these electrons up, give them kinetic energy by putting a voltage across the conductor. Okay? So this is going to be a conductor. There's a lot of space to move electrons up, give them a little bit of energy. They can occupy all these energy levels. So let's look at an insulator. What makes an insulator an insulator? A non-conductor. So let's say this is our valence band. This is energy again. This is the valence band that's created. And let's say it's completely full. It means we can't put any more electrons in it because all the energy levels are full. Okay? Holding as many electrons as possible. Full energy band. Full valence band. Cannot put any more electrons in. Well, let's say the conduction band is up here. The next available energies are up here. And there's a forbidden zone. We don't have any energy levels. There's no energy levels there. We call this the energy gap. This distance in energy. Well, that means that to get an electron at this energy to give it any kinetic energy, we have to give it enough energy for it to make it up to the conduction band. Okay? So, to give electron in valence band, energy, kinetic energy, you must give it enough energy to get up to the conduction band. Because there's no energy levels here for it to exist to have. Okay? Now, I'm also going to draw, since that's energy again, I'm going to draw what the Fermi-Dirac distribution looks like. Here's 1, here's 1/2. Now, it's over energy levels, okay? And these are all occupied. And it has to go to 0 by here. Here's the next energy level up here. So it goes up towards 0 up here. And it has this shape. So it's going to look something like this. Okay. 1/2 tends to be right in here. It tends to be about in the middle of the band gap, even though I didn't draw it well here. So this would actually be, if this is 1/2, remember what the Fermi energy is. It's the probability that you're going to have that energy level filled is going to be 1/2, right? That's what the Fermi energy means. That's the energy level, the probability for it to be occupied is 1/2. Now, this might bother you because I'm saying electrons cannot have the energy in here. But that's because we're looking at probability and here's our energy levels, and here's energy levels. Okay? Just like if I said, if I had an energy here and an energy up here, and I took the average, it would be where you couldn't have an energy. Okay? It's the same here. Since we're just talking about probability, well, there's a probability, but we're saying that's not going to happen. But according to the distribution, there's a probability. So remember, the probability is when you're looking at average, you're looking at large number of particles. And the averages, they come out. So you're like, okay, if I calculate what the Fermi energy would be, there's a probability that I would have, if I make a bunch of measurements, the energy level where I get probability of that energy being 1/2 is going to come out in between there. Okay? It's going to come out in that band gap. So the Fermi energy tends to be in the middle of the band gap. Happens. Now, this energy gap for insulators tends to be several EVs. So you would have to give this electron a lot of energy to get up there. Okay. That's going to be a high voltage probably. We haven't done the calculation, but it's going to be a high voltage to get it across there. So it's not easily going to happen. That's why we call this an insulator, okay? Since the energy, if the energy gap for an insulator (5 to 10 EVs), electrons are not going to easily get up to that conduction band, okay? So they cannot easily gain energy. have to get up to the conduction band to do that. Because there's no space available, there's no energies available here. So that's what makes it an insulator. If you have something that's configured like this, the valence band is full or almost full, and to get up to the next possible energy levels, you have to go across a wide energy gap. Okay. We're done for today, but what's going to make a semi-metal or a semiconductor is that energy gap gets a lot smaller. So you still have to go across an energy gap, but it's not near as much. Okay, so that'll be the semiconductor. We'll talk about that next time. Then we'll talk about putting what we call impurities into the semiconductor. We call it doping. I don't call it doping. Whoever invented that process calls it doping. And we'll talk about that, and then putting two types of dope semiconductors together to create something called a p-n junction. Something called a diode. We'll talk about that next time too. Okay? And next time I will give you more homework. So the homework that's due, if you want to talk to me now, we can talk about it for a few minutes. If you want to work on it a little more, go ahead, but try to get it to me soon here. I know we kind of forgot about it too. So, yeah, kind of, yeah.
And then with something like carbon bonded other things, because the fact that it's bonded other things and has like a zero formal charge, like fills the valence band then,
I'd be careful. I think that's true.
But I didn't feel for any.
no, I just think that
Yeah, I think so. Whatever solid.
that's the point. That's supposed to make any sense. If you have a bunch of like cations or something on it, it might have a chance of conducting.
I just. You got 0.88.
Yeah.
That's easy.
Well, it probably, depending, it probably has overlap in it. So it probably can conduct.
So if you have like a salt in solid form, will actually conduct it all. Yeah. But doesn't have to have the ions like associated to conduct.
Right, that just conduct, that's in a solution that does really well. Then, right? Yeah.
Work better than
Then you're just talking about the solution.
What are you doing 2.9?
But yeah, you can have a solid chunk of sodium,
Is that
for example.
well, if it's like sodium chloride, it'll still conduct.
Yeah, so we
Why is that
have huge chunks of sodium chloride downstairs.
That's
We have detectors.
That's something weird.
Made of sodium chloride.
That's probably
Sodium
good. That's
chloride
probably
crystals are like this big.
Wait,
I'll bet you if you just
They're
have
encased
that
in
again,
aluminum,
get
so you
those
can't really
answers.
see them.
Yeah, I got 1.46. Yeah.
We actually use them for detectors.
Yeah, I got 0.1 or 1.5.
Thinking that.
0.15.
Yeah, because I just didn't.
So what is the plan for the rest of the semester here as far as like we could do?
We're gonna have another
one more
test.
and
We're
then
gonna have one more
each
test and then the
course
final,
to-
which the final will include some new material and some old material.
Mhm.
It won't include every
Did you say what
the old stuff.
your value for the
So mostly for the old stuff, it'll be
So where are you getting that from?
and maybe some statistical physics, the interact, those Einstein kind of stuff.
Mhm.
So we need to figure out when the next test, since we got off the schedule, figure
Yeah.
out when the next test is going to be. It should be.
Yeah, that's what it is.
So we're starting this. We've just finished
That's what it is.
molecules, so we should probably have it when we finish this chapter. Then the next chapter is nuclear stuff.
Mhm.
So, but we ought to be on the final.
So it'll be like half nuclear, half old stuff.
Why don't I write it down? on the
Yeah,
board
I
here?
would, yeah, maybe a little less new stuff. Actually, yeah, it's probably right.
Why don't I write this down on the board?
Okay.
And then maybe we can ask him about it from there. It's kind of hard to
Alright.
combine.
Yeah, next time, so Friday, we need to probably talk and set up a date. I'm like, we don't, this chapter will go fast, there's not a lot, you're not gonna go on.
Yeah.
We're just talking about band theory, semiconductors, PN junctions, transistors, that's it, for this chapter. And, so we're done, so. Maybe 2 more days. We can think about when we want to have the test. I know that some, we don't have seniors here, right, so we don't have senior projects, those will do May 1st. Do we have anybody doing, is there anybody here doing honors talks? Probably not. So we're probably good. We could have it like May 8th or something like that.
All right.